IOU Ring is a new asynchronous API to enable fast and efficient system calls in the Linux kernel. It promises faster userland programs that make heavy use of Filesystem IO on Linux for all applications, not just databases. It's targeted towards Filesystem IO, but the interface is generic enough that you can use it for any sort of IO, whether it's network IO or other type of non-block IO.
I think it's a very interesting solution to a problem that I didn't know existed. And I can see now potentially the effects that having slow file IO has on a person who just writes normal programs. I try to keep things as much as possible in memory and then flush out to disk at the end when I'm finally done. But maybe that's just a consequence of this conditioning that the programming languages and the standard libraries and whatever don't necessarily encourage me to interact with the kernel so easily.
Hi, this is Will. I'm a YC alum and independent researcher who has worked across e-commerce, cryptocurrency, and financial industries.
And I'm Shri. I'm a YC alum and a research engineer focused on natural language processing for search.
Welcome to the Technium, where we talk about the edge of technology and what we can build with it. An optimistic look at the road ahead. We're two guys discussing edgy, fringe, or overlooked technologies over a couple of drinks. Our show has 4 segments. First, we give a high-level outline of what the technology is. Then second, we talk about what it can do today. Then we let our imagination and optimism take over and see how the world would change if the technology was readily adopted everywhere. And lastly, if we believe in this future, how can we take a position on it? Well, we can't be experts in everything that we cover, so if you got insights on that topic, let us know in the comments. And be sure to check out our audio versions on Apple Podcasts or Spotify so you can go about your day as you listen. First, in the spirit of discussing over drinks, what are we drinking today?
Today I've got Nitro Pepsi. It is a nitrogen-infused Pepsi Cola. So, yeah, here we go.
Wow, the Food Lab guys are really amping it up. I thought they only worked at Taco Bell, but apparently, well, I guess Taco Bell is a subsidiary of Pepsi, right? So they all got the Food Labs because they had the Dorito Crunch Taco, which I was like, why didn't people think of this before?
Yeah, it's getting wild out here.
Yeah. And then I got some banana and almond butter protein smoothie. I don't know if this is going to fill me up or not, but we'll see what happens here. Do you know what we're talking about today?
I hadn't heard about it until you told me about it, and so why don't you tell us?
Right. So today we're going to be talking about IOU Ring. IOU Ring is a new asynchronous API to enable fast and efficient system calls in the Linux kernel, especially promising for file system reads and writes. It's created by Jans Axbo, I think that's how you pronounce it, at Facebook. It promises faster userland programs that make heavy use of Filesystem IO on Linux for all applications, not just databases. And it's particularly targeted towards Filesystem IO, but the interface is generic enough that you can use it for any sort of IO, whether it's network IO or other type of non-block IO. So that's what we're going to be talking about today.
Nice.
Like, you are not a kernel hacker, and neither am I. Despite the beard, right? So, but yeah, I think there was a small bit of apprehension on my part because I'm like, oh, am I going to know what I'm talking about here? And so, to a degree, I think a lot of this stuff is generally one layer below where we usually work. And usually it's my opinion that occasionally we should drop down here to see what's going on, because how can we talk about the edge of technology without covering things that are a little bit outside our wheelhouse? So with that, we're going to venture forth to talk about as much as we know, and we will try very hard to be specific about what we know and what we don't know here.
Yeah, I will say I was also hesitant about going down this deep in the level of abstraction, but I've convinced myself that this is still on brand and still important for us to discuss, because if you remember our discussions about Smalltalk, which is a very, very high level language, all of those cool capabilities that we talk about at the level of programming languages and even above that, application programming, really stem from the OS level. So I think there's a holistic view of computers, which includes like even the lowest level interfaces. And so I think actually, if we delve into this, we'll see how it can really change the way that people write programs higher up the stack as well.
Yeah, I mean, I guess you're lucky so far that we haven't dived into any edge of technology for hardware, because there is where we really don't know nearly as much. I had a electrical engineering degree, undergrad degree. I really don't know that much about hardware, to be honest.
Yeah.
So maybe our viewers will see us struggling with a hardware episode in the near future. But for now, we're just going a little bit deeper in the stack. Let's talk about like what motivates this new Linux interface in the first place, because I think Linux has traditionally had system calls that were synchronous and blocking, and that was okay for most of the time. And so traditionally in Linux, like system calls from userland programs are slow. And for those of us that aren't as familiar with like kernel, like basically the OS separates out the kernel space, like kernel processes different as a separate thing from userland program. So anything that's like core to the US is in the kernel, and things that are applications that you run are usually called userland programs. And so usually like these system calls from userland programs are slow, whether it's print to the screen, access a network, read some files, or like whatever it is that you need the OS's help for. And the data from the userland program needs to be copied into the kernel space. And then the call is blocked until the kernel returns with the answer. Then that answer then needs to be copied back into userland. And so there's a lot of copying going on, as well as this whole blocking shenanigans. And so Linux has tried to have different async interfaces for a long time before IOU ring came around, and none of them felt quite right. But so a lot of programs that needed async IO, they basically implemented a thread pool in the runtime. For example, programming languages such as Go is well known for being asynchronous, but how do you do that when the system calls in the kernel are blocking? So what they do is they implement a thread pool in the runtime to task switch while waiting for the system call to return. So you follow me so far with what's going on, right? That's the state of Linux. Like, were you as surprised as I was that like most of the system calls were blocking? Because I guess like since I don't delve down here all the time, I was a little bit surprised by that, especially because the interfaces provided in the application level, like programming languages, like we have async await and promises and stuff like that. Those are all available to us. And so I was a little bit surprised by that.
Yeah, I knew that there were non-blocking IO for network sockets because I had delved a little bit into that before, but I didn't know that that set of system calls did not apply to most local file reads and writes. And so I wasn't surprised that system calls are blocking, but I knew that there was async IO supported in Linux. But it seems like it comes with a bunch of caveats and limitations, such that it's first of all not applicable to file system calls, and second, even the async interfaces to file system calls is still can be blocking in many cases.
Yeah, right. And so what Sri is talking about is the async interface called AIO, and it's supposed to be an async interface so that userland programs can do async system calls. The problem with this is that it has an annoying habit of falling silently back to being synchronous, and it's not exactly clear when it does that because it does it silently. And so for example, like I've only found I found a non-exhaustive list, which we'll put in the show notes about it. Like one, like you submitted buffer IO, but your read isn't ready in the cache, or if the write cache is full, then it'll fall back to synchronous. And so there's any number of these things that make it difficult to deterministically figure out whether your intended async call will perform as expected. But basically, you're driving from the back seat and giving instructions to somebody that might follow your directions sometimes, but most of the times can't comply directly. So
I see. Okay.
Yeah. So that's kind of like one interface, and then there's another interface called ePoll, and it's a different kind of async model. It's called a readiness model rather than a completion model like IOU ring. And the short of it is just that you have to put in the async call and the data, and then the system will notify you when data is ready. And when data is ready, then you go and read the data out, as opposed to a completion model, which is what IOU ring has, where you send the system call to the kernel, and then when it's ready, the data is already in the buffer that you provide. Granted, for IOU ring, you have to pre-allocate the buffer that it can put into, I believe, and we'll describe the exact mechanism, but the data is already ready there for you. You don't have to read it out again. So is that clear of like that was the state of the art before IOU ring came along? And so that's why like people didn't really like the async IO, and ePoll was mostly for network requests and not for the file system, because the network, there is plenty of times that things outside your system's control would put it into a state where you have to wait for something. But with the file system, like it doesn't quite make sense for something to be ready to be read, especially if you don't know what the offset into the file is yet.
Yeah, so that makes sense. So let me try to tie it back to what it means that the async interface has this limitations. Basically, the purpose of asynchronous interfaces is that you have a process, and it wants to do something that is potentially slow, right? So write to either write to a socket or write to a file or whatever it is. And so the ideal case is it says, here's this thing, go do it. And meanwhile, I'm going to process some other stuff in the thread that I have. And so I don't block on this very slow, expensive thing. Instead, my process is capable of handling other incoming data or whatever needs to be done. But the problem with this AIO, it seems, is that because it sometimes falls back to synchronous calls, it almost seems like you can't reliably, like you don't have reliable performance. Like sometimes, depending on the state of the system or how much data you write to it or the speed of the data that you're writing to it, you could have these huge spikes where you're now waiting because you're in this blocking mode.
Yeah, and apparently it's mostly databases that use this interface, is my understanding, and developers really dislike the interface because, according to Linus Torvalds, I mean, the database programmers have no taste, and they're the ones that came up with this interface. So,
I see. So then it sounds like because of this interface being so cumbersome, it's underutilized. Like this async,
it's mostly used for databases, and like other applications don't really use this for that, for a variety of reasons, I guess. One of which is that it falls back to blocking so readily.
So it makes sense to me. It doesn't sound like a great state of affairs. And I was familiar with ePoll because I, at one point in my life, was working on some real-time WebSocket type stuff. And so it was relevant to this. And but it's interesting. I had thought for the longest time that you could use ePoll for files, but it does make sense that there's a difference between network sockets and files, because network sockets, there's something on the other side which could just be waiting and have nothing to tell you for indefinite periods of time, right? And so the purpose of epoll is that you're now watching over this huge set of sockets, and you only respond when there's stuff to do. But it seems like that's not the access pattern for the file system and for disks and things. Like it's ready. It's just, it might take some time to fetch the data and page it in or whatever it is. It's not like the disk is unresponsive for some arbitrary period of time, and you need to be notified for
like the network, right? Yeah, like the network, because like it's the epoll doesn't accept file system storage files as IO at all. Like my understanding is that writing to file in Linux doesn't block indefinitely, so epoll doesn't really help much there. Like you don't really need its readiness signal mechanism, like. And so as for reading, it's hard to know when a file is ready unless it already knows like which offset to read from. And so so I guess these combination of things make epoll not a great fit for file system reads. So then userland programs and application programs are left with blocking calls in which they need to implement a thread pool on top of it to simulate async calls to the user on top.
Oh, interesting. So then basically what they do is they spawn a thread that is making these blocking calls, but then to the main thread, it pretends like it is an async interface.
Yeah. I guess that wasn't clear when I was talking about thread pools earlier. I'm glad that we're clearing this up.
Okay. Yeah.
Does that make sense? Yeah, because like you can't rely on the OS to do this for you, and OS processors are too heavyweight, and so effectively a lot of these programming languages and runtimes are implementing this up in userland.
Interesting. So that actually means that potentially there's a limit to how many files I can keep open, because otherwise there's a 1-to-1 correlation between these threads and files. Or I guess it's a pool model. So
it's a pool, yeah.
Okay, got
it. Yeah, it's a pool. So people are recycling these things when they're not being used.
Okay, gotcha.
So then the two main things is like, well, so not to mention the hard interface, but also the copying that's going on in AIO and epoll. And so IO Uring comes in and does away with both. So you not only have an interface that's comparatively easy to use, is one. Two, it doesn't do any copying, and three, it's an actual async interface. There aren't like weird edge cases in which you need to figure out as gotchas to avoid and sidestep in order to get interface. And it seems a little magical that they were able to come up with a design that was able to satisfy these orthogonal constraints. And so how did they do it? We're not going to go into too much detail, but the short of it is that they yet use another set of ring buffers. A ring buffer is basically just a place in memory in which there's no beginning or end, and you only know where to read and write based on pointers into that ring buffer. And so you can have ring buffers where you detect the end, but my understanding from the IOU ring paper is that these ring buffers are powers of 2, and it just uses the natural rollover of an integer to roll from the end back to the beginning. Does that make sense? Because like when you overflow, you just throw away the top bit and you just kind of modulate back to the beginning again.
Yes, that makes sense.
Yeah. So there's 2 ring buffers in IOU ring, and they effectively act as queues. And so one queue, aka /ring buffer, is called the SQ or the submission queue, and then one is the CQ, which is the completion queue. And so the submission queue is where messages go from userland program to the kernel. And so there, the userland program, the application, is the producer and the kernel is the consumer. Whereas the completion queue, the flow of data goes the other way, where the kernel is the producer of data, and then the application is the consumer of data in the CQ. With me so far?
Yes. So the ring buffer also, from my understanding, is in a memory space which is accessible to both the kernel
Right.
and the
Yes.
userland program. So then you don't have to copy between the two. Also.
Right. And so that's a key thing. Like that's one of the key thing. It seems like, oh, it's strange. How can you implement these zero copy sort of things across the userland kernel boundary? Well, it's available. I think it's called mmap, if I'm not mistaken. Somebody correct me if that's wrong. But basically, you're able to create shared memory between the kernel and the application. And so if you write in there, both the current user and the kernel would be able to read from there. And so for each ring buffer, there's only one writer, and so I think that probably simplifies the problem a little bit. But also they have what's called read barriers and write barriers, so that you don't get these you don't overrun or have these weird, I guess, edge cases or race conditions.
Wait, so what happens if I write to these ring buffers so fast that I flood the buffer?
Yeah, I think you're not supposed to be able to do that. Like from the paper, it was that the CQ, the completion queue, is supposed to be twice the size of the submission queue, just in case. But like it's a little bit of the responsibility of the application not to like overflow it is one. And so this I'm completely unfamiliar with, but apparently there's something called memory ordering, in which I guess it's where when you're using IOU ring, you have to set the do a read barrier call and a write barrier call, where the read barrier call ensures that the previous writes are visible before doing any subsequent memory reads. And it sounds like it's almost like a wait. So you like wait until all the previous writes are visible before you start doing like memory reads. And then there's also another call called write barrier, and then that means that you order this write after previous writes. And so I guess it's a way to order the what you do to the memory, whether it's reading or writing, so that you don't get these like weird things where, like, because it's a ring buffer, like you get some odd things that are going on when you're reading and writing in there. But to note, one more note, because it's an async interface, the results from your system calls can come back in the completion queue in any order. And so there's basically a field that you can use to associate your call in the submission queue with the result in the completion queue. But yeah, that's effectively what I'm trying to get at. That despite the fact that it's a ring buffer, there's some software precautions and guardrails in place so that you don't do funky things in the shared memory between the kernel and the user space.
Okay, that makes sense to me. But I am but a simple high-level script kiddie. My beard is
aren't we all? Yeah, our beard is so short. Our
so
beard
short.
is so short. Yeah,
I needs to be several feet longer for me to really, really grasp this thing. But if I look at it from a certain lens, I kind of see the appeal. Because if you go all the way back, rewind to blocking system calls, you can kind of think of the user and the kernel as being in this stack relationship where you have your user at the higher level of the stack and the kernel at the lower level of the stack. And when you make a system call, you kind of call in, you call down into the kernel and you wait for it to do stuff, and then it sends its results up, right? And in that meantime, while the processing is happening down in the kernel, your user program can't do anything. But if you squint a bit, and squint a lot, the IOU ring kind of looks like the user land and the kernel are two peer objects or actors. And what they have is a shared mailbox between them.
Yeah.
into
Yeah.
which they communicate through this message passing model where the
Mm-hmm.
userland says, hey, I want you to do this thing. Please do it at some point. And then the kernel says, okay, I'm going to go do this thing on a separate timeline. And when I have the result, I'm going to send the message back to the userland process with, okay, hey, here's the data that you asked me for. And
Yeah.
so if you look at it this way, the user and the kernel are kind of peers, where the kernel is just a special object or actor that has privileged access to devices.
Right. Yeah. We can go into this later, but perhaps you can write an entire OS just based on the Erlang actor model using this sort of thing. That's just me talking out of my butt, but I mean, because I don't know the first thing about everything that's required. But I mean, if this is what you need for async, then, maybe that would be something useful or interesting for people to jump on. So, but
Yeah.
I don't know if people would do that nowadays. Only the Urbit guys are crazy enough to rewrite everything from scratch. So we'll need to find another pocket of completely ambitious and crazy people to try to rewrite all that from scratch. But yeah, effectively, you're right. Like it's a way where it's a shared mailbox between the user and the kernel to be able to put messages in and then get messages back. And so one, this solves the copying problem. Two, because you just put it in and you can fire and forget, it's completely asynchronous. And then there's the default mode is that you get an interrupt from the kernel to say, okay, I'm done with what I'm doing. You can go fetch it now. And so when you go and do that, unlike the readiness model that we described before with epoll, like you don't have to then subsequently like read bytes out. Like it's already in memory for you to use in the completion ring buffer. And so you might copy it out to do something else with it or like move it somewhere else, but effectively like you can operate it on, like you have it right there and then. So that's the zero copying part. And then the other thing is the interface for IOU ring is relatively simple. I mean, like there's a setup call where you put entries into the submission queue, and then there's another one where you read it out. I think there's only 2 or 3 calls, but there's a lot of different structures and options that you put into it. And so for those of us that don't want to like fiddle with a lot of that, the Jans, I think his name, Jans. I would assume it's Jans, but he wrote a library so that it's kind of a high level wrapper, the porcelain, if you will, above this plumbing that we're discussing over here. And so I think those are the 3 things that IOU ring addresses: the copying, the bad interface, and then the async nature. And so that's how it's able to achieve it with this double ring buffer design.
Nice. That is pretty cool. I think that what would the effect for the end user be? Would it be that programs are just writing faster and reading faster from the disk, like things are just snappier for
Presumably,
file bound programs?
Yeah, presumably for IO bound programs, things should be snappier. And so one of the a lot of the web applications that we interact with have databases that back them, and usually they're made fast by throwing caches in front of them. And so presumably if databases can be faster, you can delay when you have to put in caches. So the end effect for users should be that for IO bound programs where you read and write to disk a lot, it should be a lot faster. Maybe like a more immediate one would be like people that work with gigantic media files, like say Adobe Photoshop or like whatever the Final Cut Pro, like the movie editing people. They don't have to like sit around and wait for file reads and writes. And so maybe like it should be a lot faster for that.
Yeah, that makes sense.
And so I guess like moving on to the second segment of our podcast, like what does it let us do that's new? Like what's the new thing that we can build? I think one of the interesting things that I saw was that you can chain the IO calls together in the submission queue. And so you can kind of make your own mini data pipeline there. And so I wonder if that'll have effect um, on ETL pipelines, because a lot of times they have to read a bunch of data and then stuff it onto disk. And so there's things that I imagine you could possibly do there. And then I also saw that there is a project called IOU Ring Spawn, in which the guy's working on faster build systems. And we all know how irritating it is to sit around waiting for the continuous integration system to finish your build so that, like I I had a colleague that used to work at Google, and she had the habit of having multiple clones of the repo on her machine, so that she can, while one is like compiling or whatever, doing stuff, she can work in the other repo. I was like, oh, that's kind of weird.
That's interesting. Okay.
Because you would presumably like switch branches, but because like when you switch branches, you might still have things that are like not yet committed, and like she just didn't want to deal with that, so she just cloned multiple copies and would just work between them.
Interesting. Yeah. I thought that IOU Ring had plans also to support not just file IO, but to support other types of system calls as well, so that it could just become
definitely
a unified interface for
right.
anything.
It's like the transformers that we mentioned in a previous episode, where transformers are these, I guess, AI model. What would you call it? What is a transformer?
Like a building
like an
block
AI,
for it.
building block for AI. It's been a unifying force in the AI world. So too, I think IOU Ring can be, because it's a unified interface for all kinds of IO. It's originally meant for like block level IO, but they designed it to be generic and extensible enough that it could be used for all kinds of IO.
Nice. That's pretty cool. So, and our faster build systems, are most build systems these days bound mostly by how quickly they can write their compiled objects out to disk?
I don't know that. I don't know, but
Okay.
I do know that things like make system, like make is effectively like gluing a whole bunch of system calls together, right?
Yeah.
Because you're
Yeah.
calling into different programs, possibly as part of like the build steps. And so I mean, that's my best guess. I didn't look too deeply into it, but we'll put that IOU Ring Spawn in the show notes.
Yeah. But I mean, at any rate, if you look at your performance profile of a program, as compute gets faster, and it's not getting faster at the rate of Moore's law anymore, but it's still getting faster and faster. And it's not like the compute loads are necessarily getting harder and harder. So I think that if you look at the proportion of time on a given program that is spent on file IO versus compute bound, or like how much of what proportion of your program is IO bound versus compute bound, it seems like the IO is going to dominate, right? Most programs that people write, even compilers, are pretty fast, but they might have to write objects out to disk, read them, and then link them together, et cetera, et cetera. And so it's quite possible that the limiting factor is, in fact, file IO for something like a compiler.
I don't know. That I'm not sure, because definitely there are like programs that are compute bound, right? Like games, I think, are compute bound. They typically don't do a lot of IO. I mean,
Yeah,
unless
games
they're
are
MMORPG. But I would say that there are still like large classes of programs that are compute bound. And so what we're talking about here are the applications that, I guess would be IO bound, like things that are form filling CRUD apps that web developers like that you and I cut our teeth on, I guess. So that's the sort of stuff we're talking about.
Yeah.
Yeah. I mean, like there's like ETL pipelines, and Yeah, build systems. Yeah, I don't know. Compilers, I don't know if they. I would think that they're like CPU bound, but I could be wrong. I don't know. And so I think the type of things that you can build are interesting here because there's different modes that IOU ring allows. Interrupts can be far slower if there's a lot of data to be read. So you can set IOU ring in a polling mode where the userland program just keeps polling the device driver. And there's also a different mode for kernel side polling so that the kernel will poll the submission queue to check for new entries and consume them. Of course, there's a timeout of like 1 second or something like that where it'll stop if it's not finding anything. But the fact that you can do this means that you can do I/O without making a single system call because you just stuff things into that shared memory and the kernel will pick it up and just do stuff, right? So you don't actually have to make that system call at all.
Ah, that's interesting. So kind of at the top of your program, you just say, hey, kernel, I'm going to just dump stuff in here every once in a while, read it out and do something with it. And then you, from then on, just keep writing to memory, basically.
Yeah. From then on, you just keep writing to memory. And obviously there's a timeout, but because it won't, this is not like a default setting. But you can do that. So I think that these are all interesting things that people are doing today. And so I think the immediate things that people should be able to build are faster databases because databases are, I guess, by definition, very I/O bound. Their entire job is reading and writing from disk, right? And so I think that's the initial thing. And then were there other type of immediate projects or things that you saw or heard that people are using and building IOU ring with?
No, I think a lot of the immediate use cases I saw were for things like databases. No, I haven't seen too many other use cases.
I see. I presume that that's because like both of us aren't usually in this world of like we don't attend or watch talks on the Linux Plumbers Conference or anything like that. No, I mean that's actually a conference, but yeah, I think the as application developers, I think this is probably pretty exciting to us just that we would get faster stuff with less complexity down below and we get much better guarantees, right?
Yeah.
And so moving on to the next segment of like what are the second and third order effects? Like what happens when like IOU ring would be everywhere? Because actually it made it into the Linux kernel already and it's available in the latest Linux kernels for people to use. And so that means that beyond the immediate uses of faster databases, like what do you think the second and third order effects will be when it's available everywhere and everybody is using it?
Yeah. So I'll draw an analogy to the ePoll and socket async IO world. So way back when, there used to be a challenge or some kind of benchmark called the C10K challenge. Mm-hmm. And the C10K challenge or C10K problem was this problem that somebody set forth that whether people could optimize network servers such that they could handle 10,000 concurrent connections on a single machine.
Oh, right. Yeah.
And this used to be a hard problem because prior to ePoll and this async network IO was available at the kernel level, network concurrency was achieved through spawning threads. And so you would have threads or thread pools that would handle concurrent connections, and you'd switch between them. And so you'd have software architectures or you'd have architectures for network servers similar to Apache, which were a thread-based model, and scaling those was really, really hard. And then all of a sudden, somewhere in the 2010s or something, basically, these network async IO calls made it into the mainstream kernel, and then you were actually able to have event-driven network sockets, and those propagated everywhere throughout a variety of programming languages. And the C10K problem went away. Now every standard library of almost every single modern programming language was able to have socket interfaces that could handle arbitrarily large number of connections. And you don't hear about the C10K problem anymore.
Yeah.
And so I think that it would be interesting to think about what would happen if the same thing happened for file IO, where now with this type of kernel interface, every standard programming language and its standard library will have really fast disk reads and writes. Whereas previously, this was something that needed to be tuned and optimized and was in the purview of specialized database systems. I have a few thoughts on how that could go, but I think generally it seems like there's some analogy here.
Well, so when you say fast, you mean that the throughput is much greater, but there's still like a minimum latency, right?
Yeah, the throughput being greater. Yeah.
Right. That's a good starting point to think about. Like, effectively, like what'll happen if disk access isn't so expensive? Like, have you seen that comparison of machine time to human time where they draw the analogy of how much human time it takes for each one of the access times for different levels of cache?
Mm-hmm.
And so I think L1 cache is like going to the next room. L2 cache is like going to the other side of the house or something like that. And then like going to memory is kind of like, what was it? Probably like going across the country and coming back or something like that. and then the network is like sending something on a ship and like transatlantic. I forget. Like as a programmer, I should know these. Actually, that was the point of the article, that every programmer should know these. But like I forget the details. So basically, like it's order of magnitude slower. Like a lot of these things, and like when like recently, like especially in the what's called data orientated programming, which is the idea that it's much cheaper to recompute things than to store things and cache them, because computers nowadays are just so fast. And if you can get things aligned and the L1 L2 caches warm, and like you can, it's much cheaper and faster to just recompute things from scratch than it is to like store the result, put it into memory, and then like refetch it all over again, surprisingly. Right? And so I'm thinking like maybe this brings disks like up to par with the rest of the caching system, so that it's not just such a gigantic gap. And so as a result, like maybe you could forego some of these like software techniques that we've trying to do to leverage the speed of the caches. Of course, it's not going to ever catch up, right? But effectively, like you can start to do applications that rely on a lot of IO without a lot of like trickery. Because like I guess databases lean really heavily on B trees. I don't think B trees are going to go away, but like maybe it would be a lot easier for people to write these sorts of programs. Because like before the days when we had a lot of memory, writing a spell checker was hard, but like with infinite memory or like gigantic memory, like you could write the most ineffective thing. It's easy to understand and naive, right? So like, you just scan the list because you can fit the entire dictionary in memory. So maybe it's something like that. Like I guess I'm like talking out loud and talking around it, but like what sort of things would you be like writing a whole bunch of things onto disk? I guess like video editing and like video editing is the only thing I can think of for like consumer sort of things where you might be writing a whole bunch of things onto disk.
Yeah, you might. Well, ETL pipelines also, which you mentioned before, where you have different processing stages and they write their intermediate outputs out for another to read from. And
Right.
I think that you don't, I think that's considered pretty slow. And so sometimes you might choose to write your program such that it processes things in memory and then passes it to the next step in memory. Whereas now you
Yeah.
could just use disk almost just as a persistence layer, a free persistence layer. And that gives you things like resumability. Like if your program crashed in the middle of processing something, but you
Yeah.
had written this kind of log of events, or you had written the data itself, then you could just pick back up and resume from there.
Yeah. So these ETL pipelines, you there are streaming systems in which you process a little bit of the data at a time, but there are complications that come with this. Like if you want to do aggregates, like how does that work with the sliding window, so on and so forth. Like I mean that's a separate episode and whatnot. But
Yeah.
I guess the point is that I guess the summary here it relates to a Dan Liu post. I think I read. I think it was the Dan Liu where he was talking about the Mythical Man Month, about how Fred Brooks was very pessimistic about how anything would help reduce the complexity of software, and Dan Liu pointed out that, well, no, I mean, when you have faster computers, you don't need to have complicated data structures. Like things could just be an array,
Hmm.
and you can get things done. And I think that's kind of like what it is here. I think you could possibly just do simpler things and get similar type of performance without increasing the complexity, because a lot of times the complexity is in the optimization of something where we want performance that our systems can't quite give us, so we find smart ways to reduce the amount of work that we have to do.
Yeah.
Right.
Yeah, actually, so this relates back to the point I was making earlier with network IO and network servers. So in the old days when you were writing a web server, the way that it would work is that you would delegate the responsibility of doing the network IO to a server like Apache, because it was tuned to all the tricks to handle as many concurrent connections as possible. And
Yeah.
then you would keep your program small and only write your business logic in some script or whatever. And
Wait, so what year is this that you're talking about? Is this like the early 2000s?
yeah, basically, yes.
Okay.
Yeah, early 2000s. And so you would write your business logic in some scripting language, and it would call, use some interface to call your business logic, get the output, and then send it down the socket. But you wouldn't actually know anything about sockets. You would just write your business logic this way.
Yeah.
Then what ended up happening was that because of this async interface being readily available and then incorporated into the standard libraries of most popular languages, you don't really see that model anymore. Like people are not running Apache servers that are serving their output. You actually
Inside,
just
right?
you just keep the network IO as part of your program. Maybe it's abstracted away, but basically your web server is just a part of your program that is reading and writing from network sockets. You've moved that internally into your program. Do
Hmm.
you know what I'm saying?
So yeah. So then, does that, by analogy, then are you saying that we can get the equivalent of persistent memory? I mean, like usually we persist data by writing into a database, but say like
Yeah.
we don't need the query capabilities of like the full flexible query capabilities of a database. Like we're
Mm-hmm.
just using a data structure. Like we
Yeah.
know ahead of time what our write and read patterns are going to be like, and so we choose this specific data structure. Then it might be possible to just use that and then write that directly to disk as a way of persisting it.
Yeah, that's basically I think that's the where I was going, is that, well,
yeah.
you can now, I wonder how much of the usage of database is just, I don't know all the tips and tricks to handle persistence, so I'm going to just call out to this other special program that knows how to
Mhm.
persist to disk
Yeah.
efficiently.
Right.
And now that every program gets free fast file IO, you can kind of do the same thing where you pull the database, the persistence layer of the database, at least the storage engine of the database,
Mhm.
into your program.
Yeah,
Now,
like the equivalent of having a key value store inside. I mean, like there's things like RocksDB, which is a key value embeddable key value store. But you're saying like maybe you can even forego that and just store it directly, like your data structure directly on disk because it's persisted, right?
yeah, basically. Or you could have a query engine on top of that. So I think there's a trend now to have embedded databases that are in process. So they're
Like the
obviously
SQL.
SQLite.
Yeah,
Yeah, so
SQLite.
SQLite is there. There's another one called DuckDB, which is a
Hmm.
different type of embedded database for analytical workloads.
Yeah.
Different access pattern, basically. But I think that for most, for at least many use cases that people might currently be using a special database system, they might be able to move that in process and have the persistence layer, and then maybe a light query engine that just runs in process as a library rather than calling out to a special server.
So why would you want to do that? Because that's just more for you to handle. Like, why do you want to drive stick rather
Yeah.
than like automatic? I guess is like what is, because you have to be a SQLite for this to, in some dimension, for this to be worth it, right?
Yeah, so I think that it's not like the average programmer is going to be writing the low level,
Yeah, yeah, yeah.
calling the IO ring or whatever. The same way that when you're writing in Go, you don't actually know anything about all the socket level things. But the Go standard library now just has a web server object that you can instantiate, and now you have a web server that's listening on a port, right? Like that's
So
how.
so I guess you're saying, well, yeah, yeah. I mean that. I guess maybe like programming languages, to answer my own question, maybe programming languages would have the capability to serialize and deserialize much faster. And well, I guess it depends on the design of the data structures. Like
Yeah,
I know in Python you can't pickle everything, but
right.
and so you have to design in a way that things are pickleable or like serializable. But given that that's the case, that's what you're saying, that the
Yeah.
underlying mechanism for serialization and deserialization are much faster.
Yeah, exactly. So I don't know how the interfaces will evolve in the same way that it took a lot of iterations of writing or figuring out how event driven web architectures are exposed in various programming languages. But I think that, yeah, the end goal is that your standard library might be able to now provide persistent data structures that persist to disk, and that would cannibalize a large number of use cases that people are now simply using databases for, even though they don't need all of the other bells and whistles that databases come with.
Huh. I guess it's like the trend of deconstruction of the database.
Yeah,
'Cause
yeah,
I
yeah.
was thinking, well, one, I told the story about how I failed my LinkedIn interview one time when they asked me to implement Hangman. And I just said, well, just write it to a text file. And they were like trying to hint to me that I needed to use a relational database. I mean, I didn't
Huh.
argue with them, but I mean, because like the reason why I picked it was like there was no query pattern that wasn't a known like unknown ahead of time. So that's
Right.
so I'll just write it to a text file. But and so I think the where was I going with this? So I guess it's the equivalent. Well, one, maybe if IOU ring was well known and this is like a common thing, then maybe I wouldn't have failed it. So that's a joke. But I think along the other lines is maybe along the lines of our previous episode, Datomic, which is a functional immutable database. One of the key things of Datomic is that you're able to keep the database as a local view. Like we won't get into it too much, you'll have to watch the previous episode, but when you have the database as a value, you can pass it around anywhere and it still stay the same, right? And so one of the end effect for the application programmer using the Datomic functional immutable database is that the data looks as if it was local. So like the database is not like a separate place that you go and get something. And when you like get it, you don't know if that data is outdated and changed out from under you because it's immutable, right? And so when you have that, I wonder if the same model could apply in which you have the data locally and some other mechanism to sync. And so you don't actually need the database anymore, save like a query language. But if you are thinking more like, I guess thinking more along of like Redis, right? Redis is effectively like a remote data structure storage or something, or like in-memory data structure storage. So maybe we would have more things that are more like a Redis is I think where I'm like swinging towards, if that makes any sense. Because like Redis doesn't have typical database access patterns. It just relies on the fact that it's a known data structure with specific database like data structure patterns. And so maybe it would be something like that, if that makes sense what I'm getting at.
Yeah, I think so. So basically projecting out, or to really kind of put it together, rather than making a call to a separate process and say,
over
hey, persist
there,
this
with all
over
the
there.
complexities of like the transaction, like the need for transactions and atomic transactions, so that other people aren't changing things out from under you. You have things locally here.
Yes. And potentially you have some other side process that is responsible for syncing. So it's watching this persistent data structure and saying, hey, something changed. Let me try to sync it to the network, or something changed on the network on the remote. Let me sync it here. But as far as your program is concerned, it's just reading and writing from this data structure, which is persisted locally on some file.
Right. And it should be much faster, especially if it involves like the kernel, which is supposed to be good at this stuff. Otherwise, there's no reason to have it around, right? So then like you don't need to implement this sort of stuff in Userland. You can lean on the kernel to help you with this stuff, is I guess is what we're getting at. So given that you don't need that query language, and so you just want to have that data structure locally accessible, but there's some other mechanism syncing it for you.
Yeah, that makes sense. In fact, you could have a query language. You could have a query engine that just runs in process, but it knows how to traverse the persisted data structure to find the data that it needs. So I don't think you have to forego necessarily the query language itself.
Oh, I guess you don't have to forego, but it's deconstructed. It's not like a database where like everything comes together in a vertical package. Like I guess we're unbundling the database, right?
Yes.
To quote our previous episodes.
Yeah. I think that's interesting. I don't know right off the top of my head why that is interesting, other than just the obvious thing is that it opens up the possibility for experimentation, because nobody casually says, hey, let me start a database project, and writes a whole database server with all the transactionality and the storage engine and whatever. But I think that bringing the database closer to in process and treating it like a persistent data structure allows more people the possibility of experimenting with different ways of laying out the data, different ways of querying that data, that they otherwise wouldn't. So we might see kind of this explosion of in-process databases or in-process database engines that expose
Yeah,
different novel
right.
concepts.
I almost wouldn't call them database engines because that's more full-fledged. It's like some sort of like deconstructed version. Like if the database was a
Yeah.
sandwich, like we would see more of people that only pick the lettuce, right?
Yeah.
Or like I just want to be a vegetarian. So like you come up with like what is the no bun burger, the no carbs burger in and out,
Yeah.
where it's
Yeah.
like
Yeah.
the burger between two leaves of lettuce. Like people are going to be able to do that because right now the only thing you can do when you order a burger is the whole burger with all the stuff in it,
Yeah.
regardless of like what you need it for. Like most
Yeah.
people might just need it for the persistence, or they're really leaning on the query engine or something like that, right? Because they don't know, they don't have product market fit yet, so they don't know like exactly how they're going to query and access their data, something like that. And so like I think people are going to probably be able to start to pick and choose exactly like what it is they want out of different aspects of the database. And it's not that any application programmers will write IOU ring directly, but that people that are writing these like specific slices of a database's job will be able to use IOU ring to ship that to people. So I
Yeah.
guess it's classic unbundling, right? You
Yep.
only unbundle when like the full thing is too good at its job. It's like exceeding like what you needed to do. So you just want to pick out this little slice of it and then like double down on that
Yeah.
for some other job that you have, like job to be done, right?
Yeah. 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 So I think it'd be pretty cool because you only have what, like 5 choices at most of like actual production level database systems like that are free and open source.
Oh, right. Yeah, I mean, it does make the job of like arguing with your coworkers about your stack a lot easier.
Yeah, that's true. That's true. But now anybody can write a persistent data structure library with its own query engine, and now you can have so much choice.
Right. And so you'll end up just like the JavaScript world where people write like flowcharts of the path you must take to be a systems level programmer.
Yeah,
The
right.
proliferation of all the tools that you need to learn.
Yeah.
Yeah. So I think that's kind of like one avenue that people might be able to go down. Another that kind of piqued my interest was using IOU ring to implement effect systems. And so we've only mentioned effect systems here and there on our episodes, but maybe we should do an episode on it. I don't know, but effectively, like, have you heard of effect systems? Do you know what they are?
I've only heard that people mentioned React hooks are kind of like effect systems, but I actually don't know anything about the theory of it.
Okay, right. Their typical name is an algebraic effect, but an effect system is basically where in the programming language you don't get to execute side effects directly. Like you specify a command for a side effect, and then the runtime itself will run the side effect for you and choose the right time to do it so that your code stays pure functional and all the dirty side effect stuff is handled by the runtime. That's effectively what effect systems are. They're a way for the runtime to run side effects for you so that your program can stay pure,
Gotcha.
functionally pure. Does that make sense?
Yeah, that makes sense to me. So how does that
Okay.
tie into IOU ring?
Right. And so one of the talks that I listened to about effect systems, which I thought was really a great introduction, a far better one than the one that I gave here in the short time, but it took him a long time for him to get there, which we'll put in the show notes, by Daniel Spiewik. Uh, I munge everybody's name on this show. But anyways, he was talking about how threads were a limited resource on computers for a variety of reasons, and that effect systems worked really well in mapping the side effects, the IO sort of computations that you need to do at the application levels and how they mapped to this thread pool of things that to manage the async. And so I think that IOU ring could be a very good candidate for implementing these effect systems instead of using the thread pool stuff that we're doing today, so that at the higher level, people can use these algebraic effect systems to write their write the IO aspects of their programs. So for those of you that haven't looked into it, like, you can just think of the effect systems as akin to React hooks. Like that, React hooks is partially inspired by algebraic effects.
Got you. So it kind of, algebraic effects kind of matched the shape of IOU ring in a way, in that basically IOU ring allows you to write these commands to a queue and say, hey, kernel, take care of this for me. And so algebraic effects are kind of the same thing, just at a higher level of abstraction, where you say, I want to do this thing. I don't care how it gets done. Do this thing for me. And so you can kind of just tie these two together, and now you have algebraic effects that are making use of this efficient async interface.
It seems like it. The affordance of each seems to fit well together. I could be making stuff up, but as far as I could gather, it seems to be a good application. And so that said, there aren't a lot of, I think there are no mainstream programming languages with effect systems, because I think this is one of those things that you can't quite shoehorn in. But I don't know, Java has like all sorts of stuff that Lisp had before. So like what do they have? Generics and I don't know, options,
lambdas
and all sorts
now.
Of lambdas, yeah. So yeah. I wouldn't put it past people to try to shoehorn in algebraic effects. So I mean, like, React implemented it in in the browser Userland, right?
Yeah, right.
So I wouldn't put it past people.
Yeah, that's interesting. I think that also ties into the analogy with network IO, async network IO, because the async interface that the kernel exposed ended up bubbling up to the programming language level. I think the main, or the language and runtime that popularized async network IO, at least to me and almost everybody else that I know, it was Node.js. Because the language.
We probably shouldn't end this episode without mentioning Node.js and its like reactive pattern with respect to IO.
Yeah. And so because JavaScript had anonymous functions which could serve as callbacks, et cetera, it matched very well this async IO pattern. And then other languages started to realize, hey, async IO is a good idea, but our language doesn't really support that kind of affordance, like a programming language constructs that allow us to make use of this very easily. And so a lot of languages over time have incorporated special constructs like async or await into their language. Like now, actually, Python has async keyword.
Oh, really?
Yeah.
Oh, okay.
Yeah. And they have a whole async IO subsystem to make use of this. And so I imagine that now having async file IO will propagate up into the language design a level where maybe people access it still through the async and await keywords, but maybe people will start looking into how to incorporate like effect systems to like better match the affordance that IOU ring provides.
Yeah, and remember that IOU ring is targeted. I mean, its reason for being initially was the file system, but the interface is general enough so that it should be able to encompass any sort of IO now and in the future. And so I would say it's not only for file system IO. So that's what makes me think that, it would be interesting to tie that into like general effect systems, regardless of what may come out. So you might be able to use it not just to access the network or the file system, but like any sort of devices. So I wonder if you could, yeah, like I don't know, device drivers, or like you would have generic device drivers that access these devices, and you'd be able to kind of use high level language constructs to do that. Because like right
Yeah.
now, in order to write like I don't know, something to access your USB keyboard, let's say, like to, I don't know, the ones with like the flashy LED lights, like you have to drop down a level, right?
Yeah. Right.
And so like you can't quite, as far as I know, like maybe you can do it in JavaScript. I don't know, I've never tried, but like that's not usually what people would reach for. So maybe if you have these effect systems that tie into IOU ring. I mean, the effect systems are pretty flexible. You can implement a lot of like language level constructs, such as like exceptions, I believe coroutines, other things with it. And so maybe like that, I'm definitely like talking out of my butt. But like that's the section we're in, right? Like
Yeah.
we're thinking about the future, and so maybe that's something that would be possible. Like my intuition right now says that those two would probably be a good fit.
Yeah, that makes sense.
So other than that, I mean, there's the typical run through things that, like we've already talked about, build systems and ETL pipelines. And I guess the last part is maybe like just like the things that we touched upon, like you would be able to build an actor model runtime based on IOU ring.
Yeah. I would like to see a language that exposes the OS kernel as a special purpose actor, and you just make calls to it. And maybe the use case for this is there is an actor model runtime for WASM called Lunatic, I believe.
Oh,
And
yeah.
so the idea is that you can write in any language, and you can write your actors in any language, and they all can interoperate in this Erlang type system where they can send each other messages and whatnot.
Mm-hmm.
Now, what if these actors want to do things like write things to disk? Well, one way that they can do this is in WASM, they have a standard called WASI, which is an interface for WASM programs to do things like open files and read files and whatnot.
WASI is typically when you want to run WASM programs on a server, right? As opposed to in the browser. Because typically WASM programs, which we covered in a previous episode, if you want to check that out, WebAssembly, typically WebAssembly programs are meant to be run in the browser, but because of the portability and the sandbox nature of WASM programs, people are like, well, let's just take a play from JavaScript and let's run this on the server as well. And so that's what we have. And so in order for that to work, you have WASI, which is, I think, the WebAssembly standard interface, I think, maybe.
So system interface. Yeah.
Oh, system interface.
Yes.
Yeah, so that's exactly what it is.
Yeah, exactly. So WASI is trying to provide a standardized abstraction for basically making system calls to from WASM programs. But maybe another way that you can do this is that you pretend that the kernel is an actor,
one of many actors.
Of many actors. Maybe it's a special actor that is always there as opposed to other actors, which you have to specify. And then you just talk to it over this mailbox, which of course matches pretty well with this ring buffer interface that IOU ring exposes. Yeah. And so, maybe that's an alternative to WASI or a complement to WASI.
Yeah, that's definitely interesting. Because then I mean, like Erlang distinguishes between local and remote calls. Like local calls are just functions, but like remote calls are always sent over messages. And so if things are already messages, then you could conceivably have a kernel that is remote on a different machine.
Yeah, maybe.
That sounds weird.
Yeah,
I
I
don't
don't
know
know.
what benefit you would have unless, I mean, I guess you would have OS remote and then every box is just empty. Or the OS can send itself over, but yeah, I don't know. But I guess like I'm not sure why you would want to do that at this moment,
Yeah.
but it seems like it would be possible.
Yeah, I think the main idea is to maintain some type of consistency in terms of your programming environment. So right now, if you're writing in this actor model, I don't
Mm-hmm.
know who is using a lunatic or whatever, but let's say that you're using such an actor model runtime, then you might have two ways of doing things. One way to talk to your objects that you made, which is
Mm-hmm.
through this message passing interface, and then
Yeah.
another way to talk to the underlying system, which exposes the fact that it's not an actor. You're actually making calls
Mm.
into some
Yeah. Yeah.
lower
Yeah.
level down the stack. But now everything is just an actor, and you just pretend everything is objects that you send messages to. So it kind of simplifies things.
Yeah, it's unifying. I mean, like the inconsistency is breeds complexity for sure. I mean, that's why I guess code that deals with date time will never be simplified. but
Yeah.
but yeah, I can see that. It does make it like something a little bit more uniform so that you would have just one model to be able to do anything. Because right now there's this dichotomy between like application level sort of stuff with
Yeah.
like system level sort of stuff. Like I admit, like I was surprised when I read that Hacker News, which was originally written in Arc, like that Paul Graham didn't use a database. He just wrote stuff out to disk.
Yeah.
And then like certain other functions, they were system calls like that I typically would have reached like something else for, maybe a library or something. He's just like, F it, this is a system call.
Huh.
And I guess that is, I'm not saying he's wrong. I'm saying that highlights how ingrained the idea of for me as an application developer that I would reach for libraries first over system calls.
Mhm.
Because a lot of times for bash programmers, they already live in the world of the OS, so they can reach for any sort of thing that is available in the OS. But as an application developer, I rarely go and do something like that, right?
Yeah. Yeah.
And so maybe in this way, you can actually stop writing libraries in every language and leverage the underlying OS system call.
Yeah. Yeah. Right. And the kernel kind of just becomes this peer rather than this
Right. Rather
special
than
thing.
specialized wrapper libraries or other things that are doing that work for you.
Yeah. Yeah.
And so then maybe in such a system, then it would feel more like when you're writing bash. Do you know, do you get what I'm saying? Like there's
Mm.
this, what I'm trying to get at is like there's a different feel when you're doing like mainstream programming language. Like oftentimes like things that are available to you in bash you don't really think about using as an application developer in say Python or like
Right.
Ruby or like you might make that system call because you're like but then like you have to do things that are different like in order to read back the like input output, right?
Yes.
in
So
in Ruby. And so whereas like bash is very, it's got the tools like you can use the pipe operator, whereas in like I remember in Ruby I have to like make specific things to do like some sort of streaming
right.
like stuff between the different system calls. Like that's not available
I
to
was I
me.
was trying to figure out what you meant by bash has system calls, but I now realize what you're saying is the main system call that it uses is exec, which says run a sub process and
Right, right.
get its input and output from its the respective pipes. Uh,
Right. That's
yeah,
native to bash, whereas like in other languages you have to set all that stuff up.
right. Yeah. Yes, calling out to sub processes in most languages is terrible because it does expose a weird kind of special
interface, right?
Yeah.
Yeah. And so going back to this, like if the kernel would just appear in which you just put things in the mailbox, and like any other object in your system you have to put mailbox in, then that would make it a lot easier. And so maybe you would in this type of system, you would be able to do more admin scripting in addition to application programming. So it would kind of unify the space, right? So you wouldn't have this dichotomy between people that are doing application level developing and kind of the, I don't know, like Linux administration sort of thing. I don't know if that's what application developers would want, because I know personally I hate doing DevOps. But I would like to know less, but I mean, it is powerful when you have it available. Because like for me, like oftentimes I want to have a tool or something. I have to spend forever like looking at like docs on awk or something like that, because I just don't do it that often. But if I can use whatever the main programming language to just send messages to the kernel, it could be different languages have different ways of constructing that message, but it's always like that message to the kernel, then that might make it more accessible and easy.
Yeah. Okay, I see what you're saying. Yes, so basically you can make use of the kernel as well as the other other programs that are available on your OS more easily, rather than having your OS is some world outside which is really hard to touch, and then you try to do a bunch of things inside your userland or your standard library.
Yeah, because don't you get the sense that that's the way most programs are written around nowadays? You might have like C libraries or like system call libraries that does the thing that you want, but then you just reach for some sort of like Python library that like might have implemented it in userland.
Yeah, right. Yeah, that's interesting. And I agree that probably the way that you construct those calls to the kernel might have some syntactic sugar around it, so that you're not acutely aware of the fact that you're talking to the kernel. But this, like the standard library or the runtime, is then more enabled to call out to the kernel than it otherwise would be.
Yeah, and so I feel like that would, I guess that would make us more like Paul Graham, where we just make system calls willy-nilly.
Sounds dangerous.
Yeah, I mean, I'm sure there's historic reasons why, do one way or the other. But like I said, that's just to highlight the fact that, we just like my interviewers think that the only way to get like storage is to use a database. Like the only way I think to get like some functionality is to reach for libraries rather than system calls. So
right. Yeah. I mean, I do think that the low level changes to the OS do end up bubbling up into language design. We saw it with async.
The law of leaky abstractions.
Yeah. Is it leaky? Is it necessarily bad? I don't know. I think that it's also a kind of a forcing function for language design to make use of these
hardware enhancements and
hardware enhances. So I think it could be a good thing. Like we might see some interesting innovations now if you can abstract a kernel, if you can think of the kernel through a different lens than the typical userland kernel separation.
Yeah. So I mean that's a long long winding road. Are there other things that you've thought of that you saw that we didn't quite cover?
No.
Unlike our usual selves. And so with that, like how are you feeling about IOU ring? Because I know that when we were pre-gaming and talking about like what should we cover next, I wanted to venture out in this territory. You were a little bit more skeptical. Like how do you feel after we did our research and talked through it? Like how do you feel about IOU ring?
I think it's a very interesting solution to a problem that I didn't know existed, and I can see now potentially the effects that having slow file IO has on a person who just writes normal programs. Like I I don't typically reach for the file system as just an easy thing that I can write to. Like I might write a file, that's true, but
Right.
it's not like part of the key functionality of my whatever program that I'm writing. I try to keep things as much as possible in memory and then flush out to disk at the end when I'm finally done. But maybe that's just a consequence of this conditioning that the programming languages and the standard libraries and whatever don't necessarily encourage me to write to the file so easily and interact with the kernel so easily. And maybe if you remove that friction by making it basically zero copy and async, then programming, the way that we access these interfaces through our typical programming languages will change, and the way that I write programs will change.
Yeah, I mean, I think I'm generally pretty optimistic about the effect that it has. I think other people that do more systems level work on a day-to-day than I do seem excited about it. I wanted to see what the hubbub was all about. And looking into it, I think there's some possibility out there. I think because my familiarity with it isn't as comprehensive as some of our episodes, like these possibilities were the only ones that we could come up with. But even then, like given our limited scope and understanding of this realm, I think we came up with things that seem interesting and not what people would usually talk about or think about with IOU rings. So I would say that I'm pretty optimistic at the possibilities that this can unfold.
Yeah, I guess me too.
So with that, would you say our optimism is out of this world, or it's just in the next stage?
It's building up. I want to see some concrete changes that I want to touch this thing. And right now it's still in the level of kernel hackers, but I think we might see it bubbling up pretty soon. So, and at that point I'll get super excited.
Right. You want to see $1 billion company that says we're successful because we use IOU. Right?
Yes. Right.
That'll get everybody using it. So
yeah.
Exactly. All right. So with that, our optimism is growing and about to take off, if not already. So if this episode opened your eyes, check out our other episodes as well, where we talk about other edges of technology and why they're interesting and what future they point to. Check them out and subscribe. And so be sure to check out our audio versions on Apple Podcast or Spotify and write us a review to help bring other Techniumistas on board. And with that, this is Will.
And this is Sri.
And we'll see you next time. All right, take care. Bye-bye.
Later.